Okay, let's talk about the second part. So we know that the backward limit of the limit ancient flow is round cylinder, round sphere, or plane with potential multiplicity. So first of all, I would like to get rid of the multiple plane case. So to do this, we have to introduce a non-collapsing. So non-collapsing is kind of a ratio between the main curvature and the inscribed radius. So given a closed hypersurface and any point here, we may consider maximum flow which tangent to the point, and then there's a interior flow of the closed surface. Then we say the radius of this maximum ball, maximum inscribed ball is inscribed radius. And then, we say mean convex flow is non-collapsed, and say alpha non-collapsed if H times R is bounded from below by alpha, which is positive number. And you can see that this is pretty nice quantity because it's a scale invariant, right? If the surface dilates, increase, then H decrease, but R increase for the same amount. So its multiplication remains. The multiplication is invariant. So this is a pretty useful in singularity analysis because this alpha is invariant on the blowups. And moreover, actually one can apply some maximum principle, say 2-point maximum principle for this multiplication. So if you see the paper values, then you can see that if initial data is a closed mean convex flow, if you have a closed mean convex flow, then the alpha remains. At the lower bound, alpha is determined. You have a uniform lower bound alpha, which only depends on initial data, M naught. This alpha only depends on initial data. So you can obtain this by using some maximum principle. So if you consider the blow-offs of this flow, they have a uniform alpha. So it's a blow-up limit. So limit ancient flow must be also alpha non-flushed. So this non-flushedness allow us to exclude the multiple plane case. Because, for example, I have this Green across all, then you can choose a point in the middle, then, the inscribed radius at this wall is determined by the width, the distance between these two asymptotic planes. So R has upper bound. However, if you run away from the steep lines, then the H converts to 0. So H times R converts to 0 at the infinity. So it's not alpha non-collapsed. So if you have multiple planes, then you always have this property. So you can exclude the multiple plane case. And actually, alpha non-collapsing is sort of a similar concept to kappa non-collapsing of the rigid flow. So there is some similar example. There was some potential. There is some analog to 3D rigid flow. There is a so-called Siga soliton of 2D rigid flow, which is analog to this Green-Ripper, the 1D Green-Ripper. So one have some Siga soliton cross R is a potential. It's a kind of ancient, rigid flow in our 3D-dimensional. Siga soliton cross R is 3 a three-dimensional ancient rigid flow, but that is somehow collapsed. And please see the definition of a kappa clone collapsing. So yeah, it cannot be the limit of the 3D rigid flow, closed 3D rigid flow. So one can exclude, the paradigm actually excluded the cases by using this non-collapsing. Okay, so so now we only need to consider the cases that the tangent flow at infinity is a multiplicity one plane, cylinder, or sphere. Now, yeah, we can somehow exclude, we can somehow deal with the plane and the sphere cases easily. So if the limit is the multiple one, I mean, if backward limits are planes, then somehow by direct computation, you can check that entropy of plane is 1. So it's a backward limit, so it's greater than the entropy of the flow because the entropy is monotonic decrease. However, whenever you have a complete complete and proper, say proper and complete surface, then this entropy is always greater than 1. Yeah, let me skip the details. So the entropy is constant as 1. So the plane is the only such a proper complete hypersurface with entropy 1. So in this case, we have a static plane. And then what happens if a backward limit is around the sphere? In that case, as time goes by, this ratio, kappa mean over h, converge to the n over 1 of n, because backward limit is around the sphere. However, yeah, this is close. This is a closed minimum. This is a closed surface, so closed convex surface. So backward limit is also sphere. So in the forward, sorry, plus as t equals plus infinity. No. Say singularity. Yeah. This ratio also converge to the 1 of n, the ratio of the 1 of n. And why this is monotone? That is just because it's okay. This inequality, the maximum potential. So, yeah. Okay, so yeah, so you can see that. Okay, let me say, okay, the kappa mean over h, anyhow convert to 1 of n as time goes by because they convert around the sphere. And then the problem is that and here we can consider this 0 as a negative infinity. So this one is 1 of n always. So always I have a lower bound 1 of n. But this is optimal bound. Optimal. This is actually optimal one. So always kappa mean over h is 1 of n. Okay. yeah. So this is umbilical everywhere. So it's a sphere. So shrinking sphere. And in the case that the backward limits are around cylinders, so sure there are several types of cylinders. But in this case, actually we have to concern that the flow converges to around the cylinder, but the cylinder can rotate slowly. So to show the uniqueness of tangent flow, we have to show that the limit does not rotate and then actually convert to a certain fixed around the cylinder. And that comes from the coding inequalities paper, which is kind of an analog reader to the Leon Simon's uniqueness of a tangent cone of the minimal surface at isolated singularity. Now, 1819 hours. I know, 1893 hours. Yeah. So we only need to consider now ancient convex flow, whose tangent flow is those tangent flow is unique, and then that is around the cylinder. Okay, then we can consider this rescaled guys with a rescaling time tau for some reason, for technical reason. And then actually you can just use t if you don't like tau, but yeah. And actually you have the same mathematical difficulty for using tau or t, but the only reason to use tau is to make a beautiful PDE form. Yeah, if you just consider t, then PD looks just messy, even though you have the same difficulty. Anyhow, so anyhow, so because that the flow converted to around cylinder, say sigma. Let me write sigma. Then locally it converts to locally that looks like some epsilon graph over the cylinder, and it converts to 0. Then yeah, so this below is a graphical radius, and graphical radius increase, and yeah, in the graphical radius, in the border radius row, yeah, and C2 or say C infinite sense that converts to 0. Then yeah, this scalar function U bar is satisfy some heat equation, some parabolic equation where this L is some this interaction operator, and arrow is a quadratic error. And then, but you know, this U bar is an entire one. So to consider entire case, because the cutoff function, so this U hat is 0 outside of the graphical region. So anyhow, the U hat is a nice entire solution to this kind of PD. So linear PD plus linear term plus quadratic error. So this U hat behave like a solution to a linear PD. And this L, the operator L is some very nice operator. So that is so-called the unstable Lambda operator by Powell. And then, yeah, this L is compact self-covariant operator over sigma with respect to this Gaussian density and Gaussian epsilon. So, you know, it has Eisen decomposition. So, I mean, the Gaussian L space is spanned by the Eisen functions of this L. And then, yeah, if I just consider 3D case for simplicity, because hierarchy is kind of, yeah, on the development. So, it's pretty complicated. Then, yeah, this in R3, this L operator has just 4 Eisen functions. 1, x1, x2, x3, so coding functions. And the neutral Eisen functions, I mean, Jacobi field, which is x1, x3, and x2, x3, and 2 minus x3 squared. So yeah. And then by using some very basic idea for linear PD, if you know, if you have a linear PD with operate, I mean, if you consider this a linear PD and the operator is self-fluent and compact, so you can consider Eisen decomposition for each time. Then you can find what is coefficient, the OD of coefficient. So, I mean, in that case, you know, stable eigenfunctions should not have any coefficients because you convert to 0 as t goes back. So stable guys increase backward. So it diverges to infinity, but it's bounded. So basically stable eigenfunctions vanishes. So in L2 sense, this solution U is dominated by unstable guys and neutral guys. So if you normalize it, then it must convert to an eigenfunction, which is unstable and neutral. And you can see some more details in this Angen.cover session 19 paper, which is kind of pioneering paper for this ancient study of ancient solution with spectral analysis, say stability. Anyhow, now within this case, I mean, there are several possibility that maybe it's a linear combination of 1, x1, x2, x3. And it can be also a linear combination of x1, x3, x2, x3, and x3 square minus 2, right? Yeah, but these three actually come from the choice of the rescaling somehow. And this is kind of a geometric, so we can lead up the coefficient of these guys by choosing mu center of rescaling. X3 and x1 and x2, x3 come from rotating the reference cylinder sigma. So we can also somehow show that it never appears at the backward limit. So the only possible cases is that our profile function u is identically 0, or just x3 times some constant, sure, because x3 is not a unit ideal function, or it's just a constant times 2 minus x3 squared. Only two cases. And this is somehow now interesting. So it is convex flow. So if in the middle, if u looks like some c minus 2 minus x3 squared, then it would bend like that. So in this case, it is compact. And sure, this c must be positive, because if here c is a negative, then it bend outside, quadratically bend outside, so it's never a convex. It never is not a convex. So here c must be positive. And then, yeah, to be complete. So it should be some the other case, like this. Here c is the sign of c is not important. This is non-complex case. So in Brand lecture 19, we can see that this happened when our solution is actually Bose-Einstein. You can see that if I do a asymptotic cylinder, then you can see that around the center, it looks like this guy, graph of this x3. Okay? So somehow we can actually show that, okay, in this case, it must be a Bose-Einstein. And then in the other case, if you see the Angen das Club section 20, this actually says that the solution is so-called the ancient oval. Yeah, there is some ancient solution, convex ancient solution, which is compact, but as time goes by, the isoperimeter ratio diverges. It convert, even after rescaling, convert around the cylinder. Yeah. However, this tip looks like a ball as time goes by. However, because this is convex and closed, so as time goes forward, at the forward singularity convert to a round point. There is a certain unique ancient solution look like this, satisfying this property. So we call this as ancient oval. This is not self-similar. Okay, so the limit flow. So the limit, so one more thing. So if you consider the limit flow at the first single time, it must be complete, not a compact, unless there is a shrinking sphere. And we can think about it. There's a kind of easy, interesting exercise. So at the first single point, the limit flow must be plane, around the sphere, around the cylinder, or also it's an inner sphere. So you can classify all potential flow of the closed inconvex flow. And the conjecture is R4 case. So usually R4 case is particularly interesting because for application of topology, low dimensional topology is always interesting, and 4 dimensional is the most interesting case. Anyhow, so yeah, whatever. And we can expect some similar things, but there is one more possibility that overball solution. This is a translator. I mean here, ball is ball again looks like a square. However, you know, the level set is kind of S2. So it has the O3 symmetry, maybe. Yeah. But actually, there is another type of translator. Overball. This is also a translator, but something interesting is that the level set looks like an ancient oval. So what is the difference? So in the dust bowl, look like shrinking. I mean, if you consider the level set of this guy, the height as a, if you consider height as a time, and then level slice is a time slice, then in bowl, the bowl solution is somehow at the infinity. It looks like it's just a shrinking round sphere in R3. However, bowl solution look like an ancient oval at infinity. Sure, but this bowl solution is but this oval bowl is kind of one parameter family of solutions. So yeah, this bowl solution is sort of a very special case of oval bowl though. So anyhow, again, now for this fact that the globe limited first single time to be a plane around the sphere and around the cylinder and bowl solution or oval bowl solution. And for the last thing, I would like to comment that I keep saying first time singularity. That's because I just consistently slows here, but actually somehow in some weak sense one can define some the flow beyond the singularity. So one in some weak sense it can exist even beyond the first single time. So maybe you can find some other so-called second singularity. Anyhow, whatever. So anyhow, you may consider this globe of some the singular point whose time is actually beyond the person time. Then very fortunately, even in weak sense, the non-collapse is preserved. So the global is still ancient non-collapse flow. And in that case, there is possibility that the ancient oval is also a global limit, which can be obtained beyond the possible time. Yeah, there is some conjecture. I mean, there's sort of conjecture. No one knows if there is actually some example that whose flow of limit is an ancient or not. But there is no evidence that there is no such an example. And yeah, so this was interesting question to find the example or to show the ancient oval is not living. And yeah. Okay, thank you.